Unmute myself. Find my mouse. For the record, I'm putting a link broadcasting from for now in the chat. Okay. There, and it does say sharing, but it has my audio off, so I just need to fix my video off. There we go. All right, so my talk to you today is going to be about how to find Earth 2.0, and now I don't know how to turn these dang subtitles off. Let me figure out how to set this. There, I got it. Now I got it. Okay. So I'm a scientist that studies other worlds. And you're alive at a pretty exciting time in the past quarter century where our knowledge of planets that go around other stars, what we call exoplanets, have gone from science fiction, like Star Wars and Star Trek, and to science fact. Can anyone name a movie with another world in it outside our own solar system? Avatar, right? Yeah. So the idea that other worlds exist out there is something that humanity has pondered for millennia. What? Toilet planet? Oh, I'm not familiar with that one, but yeah. So it's pretty neat. When I was your age, we didn't know of any other worlds out there. We didn't know whether or not they existed. And today we know that they are as common as stars in the sky. That really says a lot. And it's a big key step in our way into learning in our universe how common life might be. And I'm hoping that within your lifetimes, scientists will answer that question. Whether life as we know it, kind of carbon-based, requiring water to exist, hoping that within our lifetimes, we will know the answer to that question. We may get lucky and find that answer to that question in the next 10, 20 years. Otherwise, it probably will take another 50 years, but we're getting there. So first, let me tell you about some stuff here we do on campus. We have George Mason's annual Space Day. We had our first event this past September 10th. It's open to students of all ages on campus. We had over 1,400 people show up for our first one. And so we're planning something bigger and better for this coming fall, as soon as we get a room reserved on campus. The hard part is actually getting the space reserved. But we will have our second annual Space Day coming up, and last year was amazing. We had an astronaut from space. Here he is. That's me. Sorry, Dean. And we had some students. There's a student company in high school here. It's called Project Kalis. They are in the process of building their own rocket, not as a student club, but as a nonprofit organization. It's quite unusual. I have never gone to space. Unfortunately, they could probably send 2 other people in my place. So I'm a rather large individual. So I'm probably never going to make it into space, unfortunately. Probably was a dream when I was your age, and it'd be a lot of fun. And a lot of people that become professors like me do have that dream. Some of them today still try to apply to be astronauts. But one interesting thing about becoming an astronaut is that for the past 50 years, it's been something that only a government could do. And we're at a dawn of a new era where the private space industry is transforming our access to space as we speak. Now, it's still currently the domain of multimillionaires and billionaires, but that could change over our lifetime. And just this year, we might witness the first launch of the Starship rocket from SpaceX, which is going to dramatically lower the cost of access to space by a factor of 10, potentially, if everything goes well. NASA's betting on it too. They want to use it for their lunar lander later this decade. So while it has been darn next to impossible to go to space, right? I don't know how many astronauts there have been over the history of the U.S. astronaut program, maybe a couple hundred tops, and we have over 300 million people in the U.S. So literally your shots of being an astronaut are 1 in a million at best. But that could change going forward as the cost of access to space is lowered. So that's hopeful, and that's something to look forward to and exciting. You're here for our hybrid evening under the stars, where we have public talks, and when you're done and tired of listening to me talk about stuff, we're gonna go. It's a beautiful night out tonight, full moon though, so the moon's pretty bright, so we can't look at very faint things, but we're gonna go out and point at some objects with our telescope over in another building. We'll walk you over there in about 40 minutes. If you want to know more about the events that we have here on campus, we have the Mason Observatory Outreach Newsletter. My fault, we haven't put many out this academic year yet, but we also have our website. So if you just go to science.gmu.edu/observatory, that will take you to a landing page, and you can click through and get to our schedule of events. And we do have a lot of events coming up, including public nights every Thursday, Friday, and Saturday night this semester. For those of you that are interested in contributing, we do have a philanthropic organization called Patrons of the Observatory, and all donations are welcome to help continue the mission that we are doing to bring our love of astronomy and the night sky to the greater DC area community. And I'd like to thank, I copied these slides over for another presentation, so they're formatted correctly. These are some of the slides, but I'd like to thank our patrons that have donated in the past and supporting events like Space Day that we held this past fall and will now be doing every year. I can't do this by myself as the director. In fact, our deputy director was going to be the speaker today. So again, ignore the fonts on this one. But I'd like to thank our deputy director, Rob. He's homesick today. Our 3 graduate teaching assistants, Kevin, M, and Patrick, who help with the day-to-day activities. And we also have our student club. I don't see Jonathan here yet, but you'll see him later today. What? Yeah, so you're both in the student club. It's on the top 20 largest clubs on campus now today. So we got a pretty large and active student club, Friends of the Observatory. And we also have our undergraduate student guides, and Nasir was our warm-up act for tonight's show. She's one of our guides. She does an excellent job. And she'll be helping guide you on our tour of the telescope tonight. So we'll take you over. We'll give you a view of the control room and a view of the telescope, and we'll point the telescope at something nice. We have the largest on-campus observatory in the Mid-Atlantic region, the 2nd largest on the East Coast. So it's a pretty unique opportunity for you to get to see our telescope. So fun fact, I just threw this in here for fun. Did you know that the number of satellites in orbit has doubled in the last 2 years alone? Did you know that?
Yeah.
Okay, how did you know about that?
I work for the government.
Oh. Yeah, well, okay, one person. Anybody else know that? Yeah? Do you work for the government too? No? Oh, it's a big deal. And I could go give a whole nother talk on that. I do have a whole nother talk on that. And it just made the New York Times this week because it's not only affecting telescopes here on the ground, it's even affecting the Hubble Space Telescope. The radio telescopes are also impacted. Pretty much every ground-based observatory is impacted. And astronomers didn't expect to lose that battle. They're unprepared for this kind of challenge because it's become a national security issue. So in any event, for those of you that don't know about this, the number of active satellites in the last 2 years has doubled, and it's just pretty phenomenal. So much so, I want to show you what the positions of satellites in orbit look like today. And I found this animation on Twitter. Hey, bear with me for a second. I'm going to try and pull it up. This is slideshow on the fly here. This is how hot and fresh off the presses it is. The world is changing, and the sky above us is changing as well. I'm going to go ahead and find this real quick and just pop it over here. Oh, I think this is it. Yes. Okay, so I'm going to bring this over here. Oops, the other way, I guess. There it is. I'll put this in the full screen. Yeah, but this is a simulated view. Now the Earth is not shown here, but this is a batch of several thousand satellites that have been launched by SpaceX over the last 2 years, all because of SpaceX. They are on pace this year. They've launched a Starlink satellite network providing satellite internet, low latency internet, and it's a paradigm shifting event. While you might not hear this as one of the reasons, it's one of the reasons that altered the course of what has happened in Ukraine. For example, by providing internet access, traditional warfare, they might have taken out communication networks, which are ground-based. Can't take out this network. It's massively redundant in space, and it's very hard to destroy. So military loves it. Yeah. Yeah, okay. So the Earth is inside here. It's not the best animation. So the Earth itself is around 12,000 kilometers in diameter, so put that in miles. So, hey Siri, what is the diameter of the Earth in miles? So 8,000 miles across is the diameter of the Earth. Okay, now think about that for a minute. These satellites orbit around 250, 300 miles above the surface of the Earth. So they're barely above Earth, just a few hundred miles up. So small compared to the size of the Earth. This creates a shell. I appreciate your enthusiasm. So right now we are seeing a big change. So this is providing a huge mesh of satellites. Now each one of these satellites, space is big. Okay, so this is a sphere that's 8,000 miles across. It's enormous, right? But each little satellite is only about the size of this table. So they're not that big, but there is risk of collisions and all sorts of problems that I don't have time to talk about today. But I did want to at least mention that to you, that we have had a lot of changes. And the way we have been doing things over the past half century is no longer the case. We've had this huge growth in the number of satellites, and the traditional government-based approach to accessing space, probably best summarized by the launch of the Artemis 1 mission, which launched earlier this year. That each one of those missions, I think, cost something like $4 billion. And they're hoping to launch maybe once every 2 years, right? But SpaceX today is building a rocket that's just as capable, that they hope they could launch at least once a week at $50 million a pop. So substantially cheaper. So it is a big paradigm shift. Things are changing right now, right before you're under your eyes. We're having a huge change, and it's not just tourism for multimillionaires, but there's the huge potential that if we are able to lower the cost of access to space, the way we build satellites, the way we launch them could completely change. Right now, I just proposed a mission to NASA. It's a $20 million mission. The size of the thing is, the main spacecraft is about this big. And it involves so much engineering, right? Because you only get one shot at it. So every risk has to be retired. And so someone has to retire that risk, and it has to be some highly paid engineer who costs, $300,000 a year, who's doing that work. And then you have teams of them working on spacecraft. And so the costs of, even though the parts might be made of cheap aluminum or, and computer electronics, they're not incredibly expensive in terms of raw material, but in terms of personnel and design and redundancy, they can be quite expensive. But if the cost of accessing space suddenly gets down to maybe $100 a pound or $50 a pound compared to where it is now at several $1,000s a pound, then it wouldn't necessarily, need to worry. You have a lot more higher risk tolerance, and you can build and build again if it doesn't work for much less than the cost of building it once with a traditional approach. All right, so that's enough of that. My goal when I retire, is I hope to see this mission launch. This mission was selected by the National Academies as its recommendation for the US as its top mission to fly in the 2040s for astrophysics in particular. And the working name of this mission now is called the Habitable Worlds Observer. Some of you may have heard JWST just launched a year ago. It's doing amazing things. I'm not going to talk about JWST today, the James Webb Space Telescope, but that mission is launched. It's in orbit. It's doing fabulous things. It may even detect biomarkers on signs of life on other Earth-like worlds, but it's going to be a tough job and it's going to require some element of luck. But this mission that comes after it is basically a bigger and better version of the James Webb Space Telescope, bigger and capable of taking pictures of other Earth-sized worlds. And let me show you. So after it deploys, it'll look like this. Well, this is in the process of deploying, and I didn't want to finish the video here. There, so let's finish its deployment there. So it'll have a sun shield, a way to communicate back down to Earth and radiate heat away. And there you can see that telescope folding in place. That's all in animation, but it hopes someday to take a picture like this around a nearby star. Now, this isn't a planetary system where we need a black hole. This is a normal star system where we blocked out the light from the star. The stars are very bright. I mean, without the sun, we wouldn't have daytime, right? So for every 10 billion photons of light we get from a sun, we get roughly 1 from an Earth-sized planet orbiting that star. So we have to block out roughly 10 billion photons to just get that 1 photon coming from the planet. And that's what this mission is designed to do. This mission is designed to be able to use our advances in what we call coronagraphic technology to block out the light from the star to see the faint reflected light of the planets that orbit it. And this is a simulated image of what our own solar system would look like with the orbits drawn on white and labeled. We don't have giant Earth signs and arrows pointing to where we are floating in space. If those arrows and circles weren't there, they'd be hard to figure out which planet is which. But there are some important questions that we need to answer over the coming 20 years, which is how many stars gets cut off there? How many stars do we need to look at? Well, that's something that we've been answering with the Kepler mission, which I'll talk about in a little bit. How expensive does that telescope need to be? And will we know where and when to look in advance? So right now, today, if I had to pick the 100 closest stars to us and answer the question, which of them have an Earth-sized planet far enough away from those stars so that if they had water on that surface, that water would be liquid, I could not tell you today which of those stars they are. But what I could tell you is that we know roughly 1 in 10 stars do have a planet like that, statistically. So astronomers are clever. We remote sense everything. We can't go out and travel to the stars. Even if we are finding these worlds, it's not practical for us to go to them. Even if Elon Musk launches Starship and it's amazingly successful and we have colonies on the moon in 100 years, we're not going to be traveling to the stars just yet. We don't have the technology. We don't travel fast enough. The very closest star to our sun, interestingly enough, Proxima Centauri, does have an Earth-sized planet orbiting it. We do know that one does. But even then, with the best ideas that humankind has today, it would still take us roughly 40 years to send something roughly the size of a cell phone there, using laser propulsion and solar sail technology. So we're not going there anytime soon, but we are in the process of answering the question of where are they and what do we know about the presence of life on them. Let's see, what do I want to say next? So yes, I study exoplanets, and this is an example of a planet called 55 Cancri E. It is the 4th planet discovered to orbit the star 55 Cancri, and Cancri is another name for a star. It's in the constellation of Cancer, and it's just the 55th star is numbered in that constellation. This is an Earth-sized world, and we do find lots of Earth-sized worlds, but this one is orbiting so close to its star that it goes around once a day. So you would have a birthday every day on this world. You know, by the end of the year, you'd be 365 years old. But it's too hot for life. It's a bit like the lava world on Star Wars. I forget what that world was called. But it's so hot there because it's so close to its star that rock is molten into lava and is being blown away from the radiation and winds from the star. So we have a lot of different techniques, and this is probably the most technical plot I'll show. Thank you. Please. So some people would like the rest of the audience to be able to hear the talk. So this is a plot of the 5,000 worlds that we know of today. This plot's a little bit outdated. Thank you. Of the 5,000 worlds that we know that orbit other stars. And the x-axis here is what's called a logarithmic plot, which I know is not everybody in the audience has seen before. But this is the orbital period of the planet. And then this is the mass of the planet, with Jupiter right here and Earth is around down here. Yeah, so what you'll see when you look at this plot is that where the Earth would be is lonely. We actually don't have a lot of examples of Earth mass worlds and Earth-like orbital periods around their stars. And you might ask the question, is that because the Earth is rare? The answer is no, it's just the techniques that astronomers have invented to find these other worlds are very sensitive to how far away the planet is from the star. It's much easier to find them when the planet's massive and when the planet is close to the star. So we do a really good job finding planets up in here. And as we start going down this way, the smaller planets, it gets harder. We start going this way, the longer orbital periods, it also gets harder. So we're slowly pushing our sensitivity of our methods down here. But nonetheless, we can use the searches that we've done and the planets that we found here to essentially extrapolate how common Earth-like worlds are. And that's why I said the number is around 10%. Yes?
Can we see the Goldilocks zone on this chart? Or
yeah, so the Goldilocks zone for a star like our sun would be roughly about where the Earth is. So roughly a horizontal line here and a horizontal line here. So the Goldilocks zone, for those of you that don't know what it is, roughly right around here is a region where a planet in that orbit would receive enough radiation from the star that if it had a solid surface, so your rocky planet, and if it had water, that water would be in the form of a liquid. So not too hot that it would be steam, not too cold that it would be ice. Earth is in the so-called Goldilocks zone. In fact, we're at the inner edge of it. Just inside our own orbit, we have Venus, where the temperature on the surface of Venus is 900 Fahrenheit. And that's not because of, there's multiple reasons for it. One of it is a runaway global warming. Then Mars, of course, is too cold out beyond. So you'll see that we do have a lot of massive planets that orbit at the same distance from their stars that their sun do, but they're all 1 to 10 times the size of mass of Jupiter. We know those are gas giants. The gas giant planets, they don't have solid surfaces, they don't have liquid water, but they could potentially have moons that are habitable. You know, if you think of Endor in Star Wars, right? There could be, or the moons of Avatar, right? So there could be habitable moons, but our techniques aren't sufficient to be able to detect them. So that's a general idea of what we know about exoplanets today. The most common technique, the easiest technique to think about to find other worlds is the direct imaging technique that I mentioned at the beginning of my talk, where we block out the light from the star to see the faint glow of planets orbiting around it. Now, this is real data taken of the star system Beta Pictoris. Where we blocked out the light from the star here, we actually see a disk of material around the star, a lot like our asteroid belt in our own solar system, but scaled up. Beta Pictoris happens to be a really young, massive star. And back in 2003, when astronomers first looked at the system, we saw a dot of light up here. A couple of years later, it was gone. So we thought it was just an artifact of our data processing. But a few years later, it appeared on the other side. And so this was actually the discovery with the direct, we call this the direct imaging technique. We directly isolate the light of the planet from the star. To date, we've only been able to do that with a few dozen, maybe almost 50 now, of the more than 5,000 planets that we've discovered. It's a harder technique. It only works for the most massive planets and the brightest planets that orbit the furthest away from their stars. You see if there's any issues there. Hey, Jonathan, everything okay? All right. And so we were able to make a movie of this planet after it was discovered. And around 2010, which is 2015, that was the best movie we've ever had of another world. And then after that, we discovered this planetary system starting in 2009. And there's a little animation here. We found another system, HR 8799, where blocking the light out from the star, we can see 4 gas giant planets orbiting around that star, much like the Jupiter, Saturn, Uranus, and Neptune in our solar system, but scaled up. The problem with direct imaging is that it's really hard. You have to block out, in the case of those Jovian planets, you have to block out 1 million times the light from the star that compared to what comes from the planet. And there is some I'm going to skip this, complicated optics involved, and the raw data that we'll get from a telescope like Keck. Keck is the largest telescope on the planet Earth that is a fully steerable visible telescope. But we can go ahead and block the light out from the star and process it and subtract the light, in this case, to see this Jovian planet orbiting the star 51 Erie. So in the 2040s, when that mission launches, those are the types of pictures that we're going to hope to take. We're working on advancing the technology now of blocking out the light from the stars. We hope to get to the point where we can see an Earth-like world at the Earth-like distance orbiting that sun-like star. But today it's a very new technique. Not that new, actually. It's been around 20 years now, but it's very hard from the ground. The Earth's atmosphere makes things rather challenging because Earth's atmosphere is constantly changing. So we really need to go to space to do this. And that's what scientists will be doing. And we're starting to do that with JWST. JWST, though, is not sensitive enough to detect Earth mass planets. The most popular technique to find planets around other stars is the transit method. Now, most of you may know the great solar eclipse we had here in the US a few years ago, where the moon passed in front of the sun with respect to our line of sight. It's going to happen again next year in 2024. It's going to cross to path of totality. It's going to cross the US. It's going to go north of here and west of here. So you won't be able to see it here from directly in Virginia. I highly recommend going somewhere along the path of totality. The further south you can get, the better the odds are that it won't be cloudy. But I got to see the last one in totality, and it just blew my mind. It felt like an alien world I was looking at in the sky. As the sky went dark, and the light from the sun was blocked out. But astronomers basically use the same idea for around other stars. We look for eclipses when planets pass in front of other stars to see evidence of those planets orbiting them. And whose student is with this? Or whose troop is with it? Maybe we could just move them to the back or something. Give them a break. Okay. Sorry. I appreciate his enthusiasm, but I think it's becoming a bit of a distraction for everyone else. So we call this the transit method or the shadow method. We look for a planet passing in front of the star, and we see a dip in brightness. And now we do this with our telescope here on campus. So we've observed hundreds of these events with our campus telescope. And they last a few hours. And the trick is that the planet is small compared to the star. Jupiter, for example, is about 1/10 the diameter of our sun. So you think about one circle or one sphere passing in front of another sphere, it goes as a ratio of areas, how much light is going to be blocked. So a Jupiter-sized world passing in front of a sun-like star is going to block only 1% of the light of the star. But we can do that. We can detect that. And for an Earth-sized world passing in front of a sun-like star, well, Earth is about 1/10 the diameter of Jupiter. So it's about 1/100th the diameter of the sun. So it blocks 0.01% of the light from the sun. And we can detect that too today. We've been able to detect that since 2009 when NASA launched the Kepler mission to space. Can't do it from the ground, but we can do it from space. And we looked at over 150,000 stars very far away in constellations of Cygnus and Lyra for 4 years. And we detected over 1,000 planets as small as Mercury using this technique. One of the things we learned after launching this mission is that not only were Earth-sized worlds common in very short orbital periods, they were more common around stars smaller than our sun. So astronomers realized we had a shortcut to finding more Earth-like worlds if instead of looking at stars like our sun, we looked at smaller stars. So we call these stars red dwarf stars or M dwarf stars. They range in size from roughly 1/10 to 1/2 the size of our sun. So if you take the very smallest M dwarf star, you have a question? Yes. Well, none in this world. But in the universe, there's lots. And I'll come back to that in a second. I'll come back to that question in a second. It's a good question. So we launched the NASA test mission in 2017 to stare at the coolest stars in closest to us. And we have since discovered thousands of more worlds with these 4 cameras. This is showing a view of how this satellite and spacecraft works. But if you have an Earth-sized world passing in front of a very dim, cool red dwarf star, it's the alarm to read my son, probably one more of those. Bad, I'm not there with him right now. Because the star is smaller, that planet will block more of the light. That makes it easier to detect and find. And so we found some really amazing systems. One of them you may have heard in the news called the TRAPPIST-1 system. It's a system of 8 Earth-sized planets that orbit a very cool, dim red dwarf star, only 1/10 the size of our sun. And these planets are so close, but because that star is so dim and so cool, some of them are in the habitable zone, the Goldilocks zone of that star. And the James Webb Space Telescope, as we speak, well, maybe not literally, but right now, over the next year, it is taking its first views of those planets as those planets pass in front of that star. And so if you imagine our Earth, it has a thin, tenuous atmosphere. And so we're going to look very carefully how the light is absorbed by that atmosphere. We don't see the planet. We just see a dot of light and it dims. But we look at how it dims at different colors. And atmospheres transmit different amounts of light at different colors. And if we look at how the transmission through the atmosphere changes as a function of color, we get clues as to what that atmosphere is made of. So we're going to get one of our first looks at the atmosphere of a terrestrial world coming out in the next year. But the test mission was critical in discovering it. And there's that TRAPPIST-1 system showing as an analogy to our own solar system. But because this star is so dim, this entire planetary system would fit in our solar system well within the orbit of Mercury. Better analogy is actually Jupiter and its moons. This star is about 80 times the mass of Jupiter. So that's the transit method, and it's the most successful method. I'm going to skip the math, but it is the most successful method for finding planets around other worlds to date. The second most successful method is the Doppler method. It's one I spend a lot of time on. So if any of you heard a race car come towards you, or a fire engine, or an ambulance, it goes, when it goes past you, that's the Doppler effect of sound. The increase in pitch of sound as the object's coming towards you, and then the drop in pitch as it starts receding from you. Those are sound waves getting compressed on its way towards you and being stretched out on its way away from you. The same thing happens to light. Light from a star is compressed when that star is coming towards you. We call that blue shift. And light going away from you is stretched out. We call that red shift. So you might have heard the term red shift. Galaxies in our universe are red shifted because they're moving away from us. Well, astronomers figured out that if they took rainbows of pictures of stars, like here, and then these black lines are the chemical fingerprints in the atmosphere of the stars. As the star wobbles, thanks to Newton's laws of motion, in orbit, because of an orbiting planet, we will see the chemical fingerprints Doppler shift, red shift and blue shift back and forth. So astronomers, again, all we can do is remote sense. We can look at how things change with wavelength, how things change with time. We don't get a lot of information about position at all, but we try to exploit how things change in time and how things change in wavelength. And today we can detect, Neptune-sized worlds orbiting sun-like stars using this Doppler technique. Let's just skip over some of that. But this is actually the publication of the discovery of 51 Peg. This was the first hot Jupiter that was discovered in 1995. This is the data. So we're seeing the star move back and forth by velocities of plus or minus 50 meters per second. Which probably doesn't mean very much, but it would do it every 4.23 days. And when that discovery was announced, there were news reporters standing on random street corners saying, see there, there's a planet there. So I don't know if any of you are old enough to remember that day in 1995, but newscasters around the world were pointing at the constellation of Pegasus and the discovery of this first world around another sun. Today, we have incredibly complicated spectrographs and instruments to do these measurements. And so just to tell you a little bit about the projects that I'm involved with in finding other planets, well, we're going to see our campus telescope in a few minutes. I also use a telescope in Hawaii, and actually Nasir is learning how to work with some of this data. And this is our spectrograph. This telescope, and we're looking at the back of the telescope. This telescope is a mirror 10 feet across on the summit of Mauna Kea. And we are able to measure the motions of stars back and forth at jogging speeds. So we can tell whether a star is jogging towards us or jogging away from us. And as long as we have enough time on the telescope to watch how that star's velocity changes as a function of time, we can build up a picture of what's orbiting around it. And I use this to study a nearby young system called AU-MIC. And in 2020, this made CNN. I did discover that it had not one, but two transiting planets orbiting it. And what made this system special, I don't have a video. You know, I'll find the video. Let's find the video and play the video, because the video will say it a little bit better than I can about what the significance of this discovery was. It turns out AU-MIC is the second closest baby star to our sun. So we've been studying it for ages because it tells us about, sorry, getting a little bit tongue twisted here, a little bit tired. Like I said, I turned in a NASA mission proposal at like 3 a.m. Here it is. I don't think these are the right videos. No, let me find another one. Darn it. Maybe it's here. This looks like it. So we found it in 2018, and this video is going to describe the significance of this discovery. Whoops, let me turn the volume on.
Located about 32 light years away, the system will be a touchstone for understanding planetary evolution for decades to come.
Hold on. All right, now I got to figure out how. This is a little bit hard doing this. There we go. Now we can go to full screen. There we go. Drag that back to the beginning. And so this is a discovery we made right here at George Mason.
NASA's TESS and Spitzer missions have found a long-sought world orbiting the star AU microscopy, or AU-MIC for short. Located about 32 light years away, the system will be a touchstone for understanding planetary evolution for decades to come. AU-MIC is a red dwarf star at least 150 times younger than our sun. It's so young that a vast disk of dust and icy grains still surrounds it. The planet, AU-MIC-B, orbits very close to its star within a central zone where the disk material is cleared away. TESS data show the newly discovered planet is about 8% larger than Neptune, with no more than about 3.4 times its mass. TESS finds worlds like AU-MIC-B by catching tiny, regular dips in starlight called transits. Spitzer, now decommissioned, confirmed the transits during its final year of operations. The planet's host star is very young. Flares and other phenomena also alter its brightness, which complicated the search. In order to find AU-MIC-B, the science team had to remove these effects from the data. AU-MIC is a nearby laboratory for studying how stars and planets form and evolve. Studying AU-MIC-B with future missions will also tell us more about the development and evolution of planetary atmospheres. Until then, Tests will continue to hunt for more mysterious worlds, including possibly others orbiting AU Mike.
Great. So that was pretty exciting. That was a lot of fun. We also have telescope facilities in Arizona. So we're a partner in the Minerva Australis Array and Minerva North Array. And this is in Toowoomba, Australia. Just to show you a quick look at this telescope array. But it's like Pac-Man telescopes here. But it's an array of telescopes collecting spectra of stars using the Doppler technique. And then finally here at George Mason, we've helped validate and or confirm over a dozen of the worlds orbiting other stars, the candidates discovered by the test mission. So we're going to take you over there now to see that telescope and see with your own eyes, to take a look through it. But just to conclude, looking towards the future, the James Webb Space Telescope has launched. And this was an amazing accomplishment. I was actually skeptical that it would work, but it did deploy all of its 300 steps, including a sun shield to keep it cold, the size of a tennis court. And it will take a measurement of the brightness of, this is another chart. Let me tell you, this is how we're going to see life. This is going to be what the figure is going to look like if it happens with the James Webb Space Telescope. So it's going to look messy. What is this? The y-axis here is the amount of light blocked by the planet as a function of color or wavelength. And as it wiggles up and down, there's different amounts of transmission through that shell of that atmosphere. And so that tells us what the chemical composition of that atmosphere is. So if we do find signatures of life through various chemical processes going on in the atmosphere, that will be pretty exciting. And then hopefully someday, before I retire, we'll take a picture like this of another Earth-sized world. To conclude, I'm going to talk with a question, to answer a question that was had earlier about how many stars are there in the known universe. And this is a really good question. I'm trying to get out of that. Okay. The answer is actually kind of fun. There are more grains of sand. Sorry, there are more stars in the universe than grains of sand on all of the Earth's beaches combined. Roughly 10 to the power of 22, a 1 with 22 zeros after it. How can you even think about how many that is? It's incomprehensible. One of the things to know that in our Milky Way galaxy alone, there are over 100 billion stars. Okay, compare that to the population of the Earth, which is around 8 billion right now. We're still talking about 12 times as many stars in our galaxy than there are people, more than that, shoot, yeah. No, 12. Yeah, 12 times as many stars in just our galaxy alone, the Milky Way galaxy, than there are people on the entire planet Earth. And then, thanks to our studies with the Webb telescope and others, we know that there are over 100 billion galaxies in the visible universe. So 100 billion galaxies times 100 billion stars each, you end up with roughly 10 to the 22 stars. And yet, that's still less than the number of atoms in the tip of your pinky finger. So the tip of your pinky finger has about 10 to the 23 atoms, or a 1 with 23 zeros after it. So the universe is an incredibly complex place, from the very fast to the very small. And I'd like to thank you for joining us tonight, and I'll take some questions, but then we're going to head out. The question? No idea. I actually don't know. I'd have to think about it. I don't know off the top of my head. Get back. All right, can people quiet down while we take some questions? Can you speak louder, please? Well, we certainly don't compress we certainly don't use lossy compression. The data is stored on the spacecraft and is sent to the Earth via NASA's Deep Space Network, which is a series of radio telescopes located around the world that the spacecraft will point at the Earth and transmit to the Earth, and the Earth will transmit back to them. And there's a huge delay. The James Webb Space Telescope, for example, is 1 million miles further away from the Earth, further away from the sun than the Earth is. And it takes about 6 seconds for light to travel from us to the Webb Space Telescope. So we do transmit the data via radio frequencies. Starlink satellites are starting to use laser communications. That's still pretty new. And so we don't use a lot of laser communications in space yet, but it'll have much higher data rates. So eventually we will be using more laser communication. But yeah, we do transmit the data in raw format with as little compression as possible. Usually there's redundancy on board the spacecraft in case something fails, error checking codes. Random bits will get flipped because of cosmic particles striking the spacecraft. So there needs to be what are called error corrected codes to catch those instances. So it does require specialized hardware and software. In the back. So we do not yet have the technology to make it across our galaxy. That's the 8 o'clock alarm. Structured light, I think. There was a discovery that you may have seen in the news last week, that the James Webb Space Telescope found that some of the most distant galaxies we've ever imaged are more massive than we expected, than predicted by what's called the Lambda CDM model, a cold dark matter model of the universe. This doesn't break the idea that the Big Bang Theory exists. The Big Bang Theory definitely happened. But what's happened since then, how our galaxies evolve, is going to happen. Our understanding of that is changing as we speak. But in terms of traveling, I think I said earlier, it would take us 40 years with today's best technology to get to the closest star to us, which is Proxima Centauri, just over 4 light years away. If I remember correctly, a light year is around 6 trillion miles, around there. So we're talking over 24 trillion miles. And so we don't have the technology to get there at this point in time, any reasonable amount of time. More likely what we send there won't be us, but what we create in the future. So we don't have a hope at this point in time, at least we don't have any known laws of physics that allow us to travel to other stars or other galaxies on a regular basis, like we often see in Star Wars and on The Mandalorian. I watched the new episode of The Mandalorian this week, but it doesn't mean that there aren't laws of physics that we haven't discovered yet that may permit travel like that. One fun fact, so maybe someday we'll discover something like that, but we currently don't have the technology nor the theory. Well, we actually do have the theory to travel fast. It just takes too much energy to go fast enough to get there. And it's practically engineering-wise, we can't do it yet either. But someday we might, and there's who knows what the future holds. Fun fact that I wanted to say about those galaxies that are very far away. Astronomy is a bit like a time machine. The further away you look, the further into the past you're looking. When the sun sets at nighttime, when sunset tonight, the sun is 100 million miles away. And it takes light 8.5 minutes to get from the sun to us. So we see the sun as it was 8.5 minutes ago. It's not a lot of much time travel, but if you go further to the most distant reaches of our own Milky Way galaxy, our Milky Way galaxy is around 100,000 light years across. So if we look at stars on the opposite side of the galaxy, we are seeing them as they were, tens of thousands of years ago. If we go to galaxies, one of the closest spiral galaxies like our own to the sun is the Andromeda galaxy, which is around 3 million light years away. So when we get light from the Andromeda galaxy, that light left 3 million years ago to get to us. And that's why I like to tell people, when you're looking through the telescope, enjoy every minute of it, because think how far those photons traveled to get to your eyeball. Imagine if your eyeball's not there to catch them when they finally get there after that 3 million light year journey. But as we look to more and more distant galaxies, our visible universe is over 15 billion light years away. We are seeing our universe as it was being formed 10, 12, 13 billion years ago. And there was a surprise this week that with the James Webb Space Telescope, we did think that those galaxies would be small. And we see a lot of them coalescing to making bigger galaxies. But instead, we saw the bigger galaxies were already there. So that was a surprise. And we have a lot to figure out and sort out about the formation of galaxies and how quickly that happens. So it's going to be a pretty exciting time for the astronomers that do study galaxy formation. Question? Correct. Well, we don't see their light because they didn't exist. So we actually do. If you guys need to take that outside, you can go outside. Is everything okay? Yeah. Okay. All right. So yeah, astronomy is a bit like a time machine. You can look in the past. I'll get back to your question in a second. We do know, I forgot to mention, as we go faster and faster, time will travel slower for you. So it is a way to actually travel into the future, technically. But we haven't, if you fly in a plane, if you fly in space, you're a few microseconds younger than had you stayed on the surface of the Earth. It's not a lot, right? A few microseconds travel into the future, but that does happen. So we do understand mechanisms of traveling into the future, and we can see into the past, but we can't travel into the past. Getting to your question again, remind me again, because I already lost my train of thought. Yes, okay. So we can in theory look to a time when there were no galaxies and we don't see anything. But there is a time where where the universe becomes opaque. And that's where we can't see any further. And that's what we call the limit of the visible universe. Now, at visible wavelengths, it doesn't look like much. There's nothing there, but it shows up at microwave radiation wavelengths as a cosmic microwave background. And that's as far back in time as we can look. That's why we call it the limits of the visible universe. But it is this pervasive glow throughout the universe, left over from the Big Bang when the universe was around 300,000 years old. So that definitely exists, and we can't see beyond it because all the light that existed before that time was absorbed by matter. So when the universe was 300,000 years old, that's when the universe first became transparent. So we can't see anything beyond that. Now, that doesn't mean that there are more galaxies out there. We call it the visible universe. We don't actually know how big the actual universe is, and we will never know. And in fact, the rate of the universe's growth is expanding. So the amount of our universe that we see over time is actually slowly shrinking. And billions and billions of years from now, long after the sun is dead, trillions of years from now, we won't even be able to see any other galaxies because they'll all flown apart. All right, question. Yeah.
Well, is it actually like life in space?
So at the moment, as life as we know it, we have not found any strong evidence for life as we know it in our universe to date. That doesn't mean it doesn't exist. And as Carl Sagan once said, extraordinary claims require extraordinary evidence. So you've probably seen a lot about UAPs and UFOs on the news. And from the data I've been presented, there are very easy natural explanations for every video that I've seen and scrutinized. The hell, I'm curious. Wouldn't it be awesome, right? We'd love to have the prospects of life out there, but there may be some other evidence that is not released yet. We've heard rumors of that. I'd love to see it. I know someone who's working on a panel for NASA, deciding whether or not NASA should consider this a valid scientific discipline worth investigating. But most of this stuff is atmospheric phenomenon, balloons, as it were, and have artifacts of detector technology. But at the moment, we don't know. But what we do know, what we can't say, and I'm okay with not knowing. That's the fun of the thing. We're trying to find out, and we hope we find out in our lifetime. We now know that Earth-sized planets in the right locations to support liquid water are common in our universe. If there's potentially as many as 40 billion of those in our galaxy alone. So and there's also theories of physics that according to the laws of entropy, if you have a closed system, second law of thermodynamics, things become disordered. But planets are essentially closed systems with input radiation. And there are some physics theories that show that you have to dissipate that radiation through increased order. So life is potentially a natural outcome of planets like the Earth, but we just don't know yet. We don't know how often it happens. whether or not there are any existing technosignatures from civilized life. We are looking, we haven't found any. So maybe someday we will, maybe in your lifetime we will know. But at the moment, we don't know yet. But it's hard to imagine with 40 billion Earth-like planets, our galaxy alone, that there's nothing else out there. But we just scientifically don't know. We have a question up front here. Yeah, NASA shirt. Oh, we could. That's what happened to the dinosaurs 60 million years ago. So one of the things humans try to do is detect the next Earth killer asteroid. And you mentioned how is this impacted by the satellite constellations? Turns out the satellite constellations make it really hard to find those Earth impacting asteroids. No, not if they're the size of a small city. So in any event, we are hoping to catalog all the potentially Earth-threatening asteroids. Lots of small stuff hits. Just the other week, something the size of a Volkswagen van hit in between the England and France in the English Channel. We actually detected that one about 24 hours before it hit. It wasn't enough to do any damage. I mean, roughly every day, about 2 tons of space debris hits the Earth. Question? That's a good question. It's hard to quantify what there is to know about space and Earth because there's always more. And NASA at least invests pretty much equally in our study of the universe and the Earth with its climate observing satellites and Earth observing satellites. But as you probably heard, we know less about the depths of our oceans than we do about the surface of Mars. Yeah, you have an NASA shirt on, yep. All right, so why don't we start taking people over? I'll stay for some more questions. We're gonna send the first group over. Thank you for your time tonight. I hope you enjoyed the night sky views. Let's take any other questions.